Correct answer is okay. If you double your speed mathematically, you need to square both the 2 and the v. So that's going to be 4 times the kinetic energy. Good with that? Tell your neighbor. Correct answer is E, 4 times. Okay, this is the theoretical result of what you should have discovered yesterday. It might have been a little off because you didn't get exactly twice the speed. You're kind of shooting for it, but if you were to nail it twice the speed, you would go 4 times the distance. You all right with that? Okay, which this is pretty crazy. Definitely non-intuitive. Okay. One year it snowed early, and so my students were like, "Prove it." I'm like, "Okay." So we went out to the parking lot. 10 miles an hour ain't very. So that was 10 miles an hour. You have a car behind you. Yeah, this is pre-bald.
20 miles an hour. Oh, that's a 20.
Going twice the speed.
Smiling. Well, I see the school. Yeah, that's cool. 12 meters.
A little different. Okay, so went 4 times the distance. In my opinion, I think that in driver's ed, you should have some part of that as a physics course. Okay, because twice the speed, 4 times the distance is totally not intuitive. Okay, 4 times the distance, that's substantial. Okay, this is the best chart that I could find. It's not perfect, but we're going to go with it. So this is driving at 30 miles an hour. Normal conditions takes you 12 meters to stop. Snowy conditions, 30 meters to stop. Icy conditions, we're not going to school if it's icy out. Like, you shouldn't be driving if there's an ice storm. But almost 3 times the distance with 2.5 times the distance with snow versus normal conditions. Now, if we bump that up to not 60 but 50 miles an hour, Okay, normal conditions goes 53 meters. Snowy conditions 167 meters. Folks, that's a football field and a half. Okay, if you see brake lights a football field and a half away on a snowy morning, you're going to hit that person. Like if they're at a dead stop. Okay. Keep that in mind when we're going into a winter season. Give yourself some space. Think. Okay. It is. Okay. Here's a whole. Okay. Number one, better to take a tardy and get here than to die, kill somebody else, or minimal damage your car. Okay? Does that make like secondly, like um I mean and know that like as you go faster, your stopping distance is exponentially increasing. Okay? 10 miles an hour more is a substantial amount. Okay? Are we seeing that? It's not just like, oh, I'll be fine. Like, okay? Just keep that in mind when you're driving. Like, that's the numbers that actually is true. Okay? So, like, here, they're showing this yellow part's your reaction time. So, like, oh, I need to stop. Like, the time it takes you to take your foot off the accelerator and put it on the brake. This is 20 miles an hour, 30, 40, 50, 60, 70 miles an hour. Okay? Going from 30 to 60 is 4 times the distance. 70 you're like, man, it's just exponential. Good? Okay. So that's wrapping up lesson 2, going into lesson 3. So by the end of this lesson, you'll be able to describe when something has or does not have gravitational potential energy, determine when mechanical energy, how much mechanical energy something has, determine if mechanical energy is conserved or not, and how to calculate measurements when mechanical energy is conserved and when it is not. So, and creating energy bar charts. All right. Potential energy, gravitational potential energy, MGH. Where did that come from? Usually, textbooks will tell you, like, give you an example. We got this boulder on this cliff, and it has potential energy because gravity has the potential to do work on this. If this cracked and this fell, gravity would be doing work. As it fell this distance, gravity's going down, distance is going down, it's doing positive work. You okay with that? Okay. The distance this falls would be the height of where the boulder is now. So this is like force of gravity times the distance, so it would be the height. Force of gravity, way to calculate that is mass times 9.8. Substitute that in here, so you get mgh. That is where that expression came from. Potential for gravity to do work. Okay. Good with that? All right. So, looking at a book on a table. I'll spare you the calculations. How much gravitational potential energy does it have at this location? It could be any of those. Okay. If you defined ground zero, it all depends on where you define ground zero. If you define ground zero to be the tabletop, then it has no potential energy. It's at ground zero. If you're like, well, it could fall and hit the ground, okay, then you define this as ground, the floor is ground zero. But then we consider, well, wait a minute, we're on the second floor. What happens if we had an earthquake and like the floor ripped open and like it fell all the, okay, sure. We could call the grass outside ground zero. Okay, so it all depends on what you define as ground zero. So how do you know what to define ground zero? The answer to that question is make the lowest point that you care about ground zero. Make the lowest point that you care about ground zero. So if the book stayed on the table, the lowest point you care about is the tabletop. So make that ground zero. If the book falls off the table and hits the floor, the lowest point you care about at that point is the floor in the classroom. If we chucked it out the window, the lowest point we care about is the grass outside. So make that ground zero. It all depends on your scenario. Okay? Answer that question. Thumbs up when you have a guess. Have a conversation. Tell them why you think so.
Because the higher
Okay, what do you say? What do you say? Yes, no, maybe so? Okay. Mechanical energy is conserved if there are no non-conservative forces doing work. There's no non-conservative forces doing work. What forces are acting on this letter? Gravity and normal force. Okay? So you have gravity and normal force. Okay. Is gravity a conservative or non-conservative force? conservative force. So we're good with that. Is normal force a conservative or non-conservative force? Got non-conservative, like uh-oh. But it's not if a non-conservative force is acting on the object, it is if it's doing work. Is normal force doing work on the sledder? Is there any component that is parallel to the direction of motion? Is any component of normal force that is acting parallel to the direction of motion? No, it is acting perpendicular to the direction of motion. Therefore, it does no work. So if mechanical energy is conserved, if there are no non-conservative forces doing work, in this example, is mechanical energy conserved? Thumbs up, yes. Thumbs down, no. Correct answer is mechanical energy is conserved. There's no conservative forces doing work. Sorry, no non-conservative forces doing work. Good with that? Okay. Give that one a shot.
You're gonna love it.
Tell your neighbor. Correct answer is? Okay, forces acting on this. Gravity. Is gravity conservative or non-conservative force? It's a conservative force. So we're okay with that. Normal force. Is that a conservative or non-conservative force? Non-conservative. Is it doing work on the car? No, it's acting perpendicular to the car. Perpendicular to the car's motion. We have applied force. Is applied force a conservative or non-conservative force? It's a non-conservative force. Is it doing work on the car? Is there any component of that force that is parallel to the direction of motion of the car? Yes. Is applied force doing work on the car? Yes. So, is mechanical energy conserved? No. There is a non-conservative force doing work on the car. Mechanical energy is not conserved, but it's moving at a constant velocity. Yes, yes it is. And you know the sum of the forces are equal to 0, but that does not say anything about if mechanical energy is conserved or not. That is a completely different condition. Okay? Here's what the parts of mechanical energy have: kinetic and potential. Here, the potential energy is decreasing. because you're decreasing elevation. Your kinetic energy is remaining constant because you're moving at a constant velocity. What should happen if mechanical energy was conserved is as potential energy is decreasing, kinetic energy is increasing. And that did not happen here. Okay? All right. So if mechanical energy is not conserved, does it change or does mechanical energy stay constant? If mechanical energy is not conserved, does mechanical energy stay constant or does it change? It changes. If it is not conserved, that means it doesn't stay the same, it changes. How do you calculate the change in anything? Final minus initial. Is everybody okay with that? Now, what I've discovered is students don't do so well when there's a negative sign in things. Okay, it just messes with you. So here's my proposal. I'm going to get rid of it by bringing this over here. Okay, so the initial plus the change is equal to the final. I just took that, brought it over here. Everybody right with that? No more negative. Okay. Now, the work done by a non-conservative force is equal to the change in mechanical energy. Right with that? So what I'm going to do is I'm going to employ that, and I'm going to take that, and I'm going to use that to substitute in for change in mechanical energy and substitute in work by non-conservative force. And then I'm going to remember that mechanical energy is the sum of kinetic plus potential. So if I took that and substituted that in here, I've got initial kinetic energy plus initial potential energy plus the work done by non-conservative force is equal to the final kinetic energy plus the final potential energy. Okay? And that, my friends, is going to be your best friend, this unit. That last step here. This is going to be your original equation for many of the problems that you're going to be doing. Like 85% of the time. Cool with that? So let's learn how to use it. All right. I recognize that this animation is pretty archaic, but there's a lot of good stuff in here. What this shows is an animated bar graph. What happens to kinetic energy, potential energy, work done by a non-conservative force, and your mechanical energy. Okay. So initially, the skier is on a frictionless slope. You have gravity, it's conservative force that we're good with, And you have normal force, which is non-conservative, but it's acting perpendicular to the direction of motion. So as the sledder goes down the hill, is mechanical energy being conserved? Yes. Okay, so here's what that looks like from an energy point of view. Initially, you're starting up top, so you have a lot of potential energy. And as you go down in elevation, you're decreasing potential, but you're speeding up, increasing kinetic. But the total mechanical energy stayed conserved, stayed the same. It was always there until you got to the bottom and you have force of gravity, normal force, and force of friction. Conservative force, non-conservative force, but not doing any work. Non-conservative force, but doing work. Is it doing positive or negative work here? Negative work. It's acting in the opposite direction of motion. Notice what happens to the mechanical energy when you do negative work. Wait for it. Negative work is happening. We're losing mechanical energy. However much work is done, that's how much mechanical energy is changed by. Cool with that? Okay. I want you to sit here and marinate in that for a little bit. There's a lot of good stuff to like make connections with. Any questions at this point in the ball game? Okay. So usually we don't have animations. Kind of stuck with something like this. Okay. As the block slides down the incline, initially it has a certain amount of potential energy and it starts at rest. So zero kinetic. But as it slides down, it speeds up. But the total amount of mechanical energy is still 100 joules. Good with that? So at some other point down the way, you have 75 joules of kinetic energy. How many joules of potential energy do you have? There we go to 25. That makes sense because the total is still 100. And so by the time you reach the bottom, you have 0 joules of potential energy and how many joules of kinetic? 100. Good with that? It's a pretty basic example, but it kind of gives you a working, gives you some numbers. Okay. So with these pennies that I've passed out, energy and money is a great analogy. Okay. You're gonna put your money in a bank. Okay. And in the bank, you're gonna have a checking account and you're gonna have a savings account. Okay. So on your desk, or on a note, on your piece of paper, draw a little square section that says checking and another little square that says savings that your pennies could fit into. Okay, if you draw it on the desk, just make sure you erase it. Okay, it's just a little square. All you're doing is this. You're like, here's a little section. I can stick a penny in there, and this is checking, and this is savings. That's all you're doing. Okay, so this is going to represent your kinetic energy. This is going to represent your potential energy. Okay. On your bank statement, it's going to say, here's how much you have in your checking. Here's how much you have in your savings. Total, you have this much. The total is going to be your mechanical energy. So what you have is your net, like your gross amount, like your total. Good with that? Now, if you spend money, take money out, you withdraw money, or you deposit money, that's changing how much mechanical energy you have. That would be a work done by a non-conservative force. If you're taking money out, that's a negative work done by a non-conservative force. If you're adding money, you're depositing it, that's work done, that's positive work done by a non-conservative force. Taking money away, sorry, it's taking energy away or it's adding energy. You all right with that? Now, if mechanical energy is conserved, all that means is you did an internal transfer between your check-ins and your savings, but it didn't change it at all how much money was in the bank. Is everybody good with that? You see how the analogy is kind of setting the stage here? Okay. So let's employ this. So remember the 5 steps that I had you do for setting up last chapter with free body diagram? Okay. Here are the steps that you're going to do for working energy. Step number 1, you must define your initial and your final positions. Have to define your initial and final positions. Okay. So in this scenario here, with the slider, initially it's going to be at the bottom, and finally is at the highest point. That's my initial and final conditions. You remember the question about the truck doing the U-turn, 60 miles an hour, 60 miles an hour? It totally depended on what we defined to be our initial and our final spots. Determined, hey, is this positive work? Is it negative work? Is it zero work? It totally dependent. So it's essential to define your initial and final locations. Second step is define ground zero. Where is ground zero? The answer to that question is the lowest point that you care about. Looking at initial, final, the lowest point that you care about between those two is your initial for this example. So I'm going to make this ground zero. Good with that? Make the lowest point you care about ground zero. Step 3, you need to figure out what type of energies you have at the initial and the final locations. Okay? So what type of energies? What energies are present? To answer this question, you're saying, is there kinetic energy? To answer that question, is it moving at that location? Okay. And potential energy, you're asking yourself, is it above ground zero? You're asking yourself, is it above ground zero? Okay. So let's start looking at this example. At the initial position, do you have kinetic energy? In this example of this letter, do you have kinetic energy? Thumbs up, thumbs down. At this location here, do you have kinetic energy? Are you moving? Is it moving? Yes. You have kinetic energy. How much? I don't really care at this moment in time. We have it. So from a bar chart point of view, so what I'm going to try to do is kind of like recreate this scenario, but like take snapshots at the initial and the final. Okay. So I have kinetic energy. How much? It doesn't matter. So put make a stack of pennies and put it in your checking square. Okay. Doesn't really matter how many. It's just there's money in your checking account. There's energy and kinetic energy. Okay. Do you have gravitational potential energy? Do you have potential energy at the initial location? Is it above ground zero? That's what you're asking yourself. Give me a thumbs up, thumbs down. It is at ground zero. So no, it does not. So your savings account has nothing in there. So your total balance initially looks like this. Your kinetic energy plus your potential energy. So however many pennies you had in your checking, that's how many pennies you have total in your bank. Good with that? Okay. Step 4 is to determine, hey, is there any work done by a non-conservative force during this process from the initial to the final? Okay. We've discerned previously that there is no work done by a non-conservative force. Okay. So we did not take any money out, nor did we put any money in. Okay. So the work done by a non-conservative force is zero. So anything that's going to happen is an internal transfer. Okay. At the highest point, do you have kinetic energy? Thumbs up, thumbs down. The highest point, do you have kinetic energy? The highest point, you stop. That's why it's the highest. Okay. So you do not have kinetic energy. Do you have potential energy at the final location? Thumbs up, thumbs down. Okay. Are you above ground zero? Yes, you are. So you have potential energy. How much potential energy do you have? Well, check this out. Okay, here's the connection here. So here's what we started with, our initial total amount of money. Here's the process from the initial to the final. There was no money deposited or taken away. So the total amount of money in the bank is still whatever you had. Does that make sense? So you have no kinetic. How much potential and energy do you have? Whatever you start, like it was completely transferred. Oh, that was a squished penny. There we go. Okay. All that went into potential. It got transferred from the checking into the savings. Good with that? Okay. Now, to kind of a follow-up question. Give that one a shot. Tell your neighbor. Okay. Did kinetic energy, was it gained, lost, or stayed the same? From here to here. We lost kinetic energy. Was potential energy gained or lost? Going from here to here. Potential energy was gained. Okay. So in this scenario, if mechanical energy is conserved, the change in kinetic energy will always equal the change in potential energy. It's an internal transfer. Whatever, like, does that make sense? Well, like, whatever came out of one goes into the other. It stayed in the bank. It was conserved. Good with that? Okay. We'll call that good for today. That's as far as we got.